Hi all, that's me again, Dr. Aman. This is going to be the third part for the chapter 5 of the refrigeration cycle. So we have looked on the actual refrigeration cycle before. So in here, I'm going to present you the improvement that can be made in order to increase the coefficient of performance. So basically, there are three types of the innovative of the compression refrigeration cycle, which is we're going to look for the cascade refrigeration cycle, multi-stage refrigeration cycle, and the vapor compression refrigeration cycle. So in this third chapter, we're going to look on the cascade refrigeration cycle. Ammonia is commonly used by the industry. It's not toxic, but it is the odor. It is not comfort. Yeah. And then sulfur dioxide and ethyl chloride is another toxic refrigerant. CFC is widely used, but it is harmful to our environment because it is content of the freon. But however, it is a low cost, yeah? So it is harmful to our ozone layer because it can deplete, it can react with our ozone layer and then decrease the ozone layers sections. So the consideration for the selection of the refrigerant, you have to suit with the temperature of the refrigerated space and the surrounding, and as well it shouldn't be non-toxic, non-corrosive, chemically stable, and non-flammable at low cost conditions. In general, there are three types of the refrigerant. So the first one known as the wet refrigerant. Okay, wet refrigerant. So this is a temperature entropy diagram. Wet refrigerant, usually the curve is like that, is a normal that you have seen before. But another one known as the dry refrigerant. Okay, dry refrigerant is the temperature entropy diagram is like this. Okay, so if you have the expansion in this condition, it will go from the superheated region, sorry, saturated vapor, and then will expand to the superheated region. Okay, and then finally we also have the isentropic, where the temperature isentropic curve is like this, where it is almost isentropic for the saturated vapor sections. Okay. Then vapor compression innovative system that we have is the cascade refrigeration system, where through this cascade refrigeration system, the cycle been divided or been split into two stages, which is a top cycle and bottom cycle. So top and bottom cycle is connected by a heat exchanger. So the condenser from the bottom cycle will be connected with the evaporator for the top cycle in the heat exchanger, where both of the bottom cycle and top cycle, the working fluid is a different cycle. So it can be a similar working fluid or it can be a different working fluid. So for example, if we have this temperature entropy diagram, so what we have here is that after the expansion of the from the state 1 in the compressor, so compressions state 1, and then we go to the condenser, and then condenser from the bottom cycle we reject the heat to the in the heat exchanger, where the evaporator in the heat exchanger will absorb evaporator for the bottom for the top cycle in the heat exchanger will absorb the heat, and then will be expand into the and will be compressed into the compressor, and then the heat will be rejected by the condenser into the warm environment, and then expand in the expansion valve, As for the bottom cycle, the expansion valve expansion is in this process and then come back to the evaporator. So the evaporator for the bottoming cycle will absorb the heat from the refrigerated spaces. So what is the advantage here is that it will increase the refrigeration capacity, and then the power input for the compressor can be optimized, because the compressor will be lessened in terms of the power input. Okay, so the decrease will be happen in the compressor power. So the power input for the QL, the heat for the rejection from the QL from the QH for the bottoming cycle will be equal to the QL for the upper cycle. So which is the m dot H2 minus H3 equal to, this is m dot B, equal to m dot A H5 minus H8. So this can be simplified into these equations, where finally we can find the ratio for the mass flow rate of the bottom cycle, to upper cycle to the bottom cycle, which is given by the enthalpy change across the condenser for the bottom cycle and evaporator for the top cycle. So from that we can define the coefficient of performance, whereby from the temperature entropy diagram before that you have seen the amount of the rate of the heat exchanger, rate of the heat transfer from the evaporator has been increased, and then the work net or the power for the required for the compressor has been decreased. So we are expecting here the coefficient of performance from the cascade cycle will be increased. So this is another example that we're going to discuss during the class, during our synchronous class. Please attend the class later, our Google class. Okay.